Okay, so I've made a few videos on the side project. This is a multi-class image classification project deployed to Google Cloud. It's all automated, and it uses something called continuous training to take a base model and train it with new data that's generated from the system, something called data flywheel, and then iteratively improve off of that base model with subsequent versions of the model. I've found, and you can see that visualized here. So my first base model, which is just out of the box, does really well. It's trained on ImageNet, which contains tons of dog images. And then I create a new version of the model off of that base model. I have to change the classification head because the my source of truth, which is just an open database of dog images, uses different labels and has a different number of classes. But there is some overlap, so there is some transfer learning that I can apply to these fine-tuned versions. And so what I expect to see and what I'm seeing is as we add more data from this data flywheel effect, each version of the model gets better and better. There's a big jump here because of some manual testing I did that made the data set for this model version end up being a lot bigger. But the general trend is what I expect us to get better over time. What I'm trying to understand more is how data set distribution affects this. Um, so, let's say the data set between model 3.3 and 3.4, their distributions differ a little bit. So I'd like to track those distributions and understand how that affects model performance, so that I can uh, think about improving my model tuning, not just by giving it more and more data, right? Because that would work. But what about focusing on images or classes for which that particular model is doing poorly, right? And so what I'm doing is for each version of the model, I track its correct and incorrect predictions, and then I curate or create a data set through data flow of specifically for those incorrect predictions. But something that might bite me is um, creating skew. So like maybe this model did poorly on certain uh, classes, and this model didn't do poorly on those classes, and so this model is going to contain a lot of examples of the classes for which this model did poorly on, and so it could cause the performance of your model to kind of like bounce back and forth between the distributions. And so one version of the model might do really well on one distribution or set of class breeds, and the other might do better on another set. And we never really dial in this performance to continuously improve. So in order to dig into that and better understand it, I've created a panel. So I'm outputting all of my data set metrics to BigQuery. And so this happens in my data processing pipeline in Apache Beam. We create something called a do function, which will just take um, label and label information output from a previous pipeline transform, and then write that data to a BigQuery table. And we won't get into how Apache Beam works in this video, but we will soon. And then I can query my dataset distribution table and create metrics or create visualizations like this. So this is just a visualization of the training dataset distribution for a particular version of my model 3.3 grouped by class name, right? And we can see kind of like this Klumer dog breed had a lot of examples, 33, and then this Indian Chipperai had very few. And then so we can look at this when we're trying to assess the performance of each version of the model. And furthermore, we can use something called KL divergence which is related to entropy. And it basically, you take one probability distribution P, compare it to Q, and it'll tell you how much different Q is from P, how many pieces of information needed to be added to P to equal Q. And so in this first version of creating this data set monitoring component of my system, I've just used the 3.1, the data set for model 3.1, which we can see here. This is a bar graph visualization of the data distribution across all the classes in the task. I use that as my baseline, and then we compute a KL divergence from that baseline distribution to subsequent distribution. So the divergence for 3.1 should be 0. It's going to be greater than or equal to 0. And the closer to 0, the better. So if you have a value close to 1 or greater than 1, that's like a huge divergence. And so we can see there's a huge divergence between 0, between model version 3.1 and 3.2. And that's because I was doing some testing and um, allowed model version 3.2 to have a really poor data set distribution. Like that, this is a very small number of samples. I don't even have all of the classes represented here. So we expect that to be quite high, meaning high divergence. And then for these other examples, it's a little bit lower. And so the idea here is I can create, what I'm going to do is create a baseline data distribution that has, say, 30 or 40 examples for each class, and then use that as my baseline, and then compare every subsequent class to that baseline to see how it diverges from this kind of very equally distributed data set. And then that'll let me kind of gain or infer the effects of my data set distribution on the performance of my model, separate from just total number of examples. Because we know if we increase the number of examples, the model will get better at predicting classes for which we have more examples. But I'd like to focus the training and the data set creation, instead of just creating more and more examples, to be a little more intelligent. And one of the reasons is for some of my recent training runs, I was running my virtual machine that the training runs in on Vertex AI was running out of memory. And so when you're running these training runs with TensorFlow, you're going to read a lot of images into memory and process them, and that can take a lot of compute or memory. So instead of having to make it, scale up my virtual machine as my data set gets bigger, I mean, which I'll probably have to do eventually anyway, I want to focus on getting the maximum amount of gains I can out of the limited resources I have. I'm just using a very small virtual machine for cost purposes, and I want to understand what are the kind of like hyperparameters I can tune around my data set that'll allow me to improve the model without necessarily just keeping doubling the size of my data set. And so that's kind of what I'm doing here. So what this will require me to do is to create a base data set. What's cool about Apache Beam is I can do that in Apache Beam. I have tens of thousands of data images I've collected through running many different iterations of the system. And so I can use something like Apache Beam to define what are called pipeline transforms and do functions. And what a pipeline transform does is it takes as an input, it takes a P collection, which is essentially just a distributed data set, similar to, I think, like a reliable distributed data set, it's called in Spark. But it's just a data set that can be partitioned and spread across multiple worker machines or nodes, and then you can apply transformations. So in this case, I created a simple uh, uh, P collection, which just lists the paths I want this this program or this transform to use, and then it just goes and uh, applies a do function, which essentially just says list all the blobs, the GCS um, um, images, the images in GCS for this particular bucket, right? And so this is just the starter code for what I'm going to do, which is establish a baseline data set. So I'm going to create maybe 30 examples for each class. So this will read all my classes, iterate through, and collect 30 of each separate class until I have 30 of every 162 classes output to a base data set, which I'll use as my comparison for this KL divergence metric, which will give me better insight on how I'm curating, because I've also have code that creates the data set for each of these models, and tuning that to be closer or maybe intentionally further from this baseline distribution can give me an idea of how to make each data set um, give what the next version of the model really needs to improve. And this all could be really wrong. I don't know, maybe. But anyway, just to kind of demonstrate this, how fast this is. So what's great about Beam is you can use something called a direct runner. So I don't need to run this in the cloud. I can test it locally and then change some of my pipeline options, and the same exact code will run in Dataflow in Google's managed Apache Beam service. And locally, I have a fairly beefy machine, so I can use multi-threading and create specify a number of worker threads to use. So this, I think I have like I don't know, 40 or 50,000 images in GCS. So I can do UV run or Python, but I'm using UV to manage my packages. I can UV run um, this program, and you'll see it's very quickly listing all of these breeds, and it'll do that for all of the images, the tens of thousands of images in my um, GCS bucket. So that's really cool. Try to get this to cancel. That's a really cool way to create this base data set. And then once I have this baseline data set, I can either update that based on something called I think there's something called curriculum learning, which is designed around curating data based on what your model is good at predicting versus bad at predicting, and trying to um, kind of create a curriculum where you give it easy training data that it's easily predict, and then maybe for classes that are a little more difficult for the model to predict, you add those in as the model gets better at those easy images, and you try to retain its ability to predict those simpler breed types while you're tuning it on more complicated or hard to predict breeds. So yeah, that's a lot of stuff. Um, this is really fun doing, and so I hope you uh, got something out of that. And if you do, that's dope. If you want to know more, have a question about something in particular, just hit me up, message me anytime.